Alright, so let's dive into the DNS message format. So there's only going to be one single DNS message format, and it's going to be used for all types of DNS messages. So that could be queries, responses, zone transfers, notifications, dynamic updates, what have you. It's all going to use the same message format. So we have a header, and that's going to be 12 bytes. That's going to be a fixed size. So the header size is never going to change. However, we do have 4 variable length sections. And the sections are going to be questions, which are queries, answers, authority records, and additional records. So also note that all but the first section are going to contain one or more resource records. So the question of the query is going to say, hey, I need to know this information, and the rest of those are all going to be different record types. And so we'll get into the record types here in just a bit, but ultimately it's going to be a way for us to provide those answers to either another DNS server or to the client. So the DNS header, so we have this transaction ID, and that's going to be 16 bits, and that's going to be set by the client. It's going to be returned by the server, and so it's going to allow the client to match the responses to the requests. So we've talked about this quite a bit now with all the various messages and protocol types at various layers that we've dealt with. And so it's this idea of multiplexing. We need to be able to separate out traffic from one thing to another thing to another thing to another thing and keep it all straight while utilizing the same networking infrastructure. So then we have the QR field, and that's going to be 1 bit, and it's going to be 0 for query, 1 for response. Easy enough. Then we have the opcode, and that's going to be 4 bits. And so the most common values that we need to be aware of here are going to be 0, which is a standard query, and we have 4 is a notify, and 5 is an update. So values 1 through 3 are going to be deprecated, no longer used. So 0, 4, and 5 are going to be what you need to concern yourselves with here. Then you have the AA field, which is the authoritative answer. That's going to be 1 bit. And again, 0 is not authoritative and 1 is authoritative. So we mentioned before that name servers are authoritative for a specific zone. Well, we do have this thing called DNS caching, and that helps us to serve up answers to various pieces of information from a particular zone without being a name server for that zone. So for instance, if we query out to google.com for www, that's going to be marked as a 1 or a true because that is an authoritative source for that information if we are contacting the name server. However, if we are getting that information from our DNS server because it's cached information, then it's going to return a non-authoritative response to that because it's not the name server for that particular domain or that zone. Then we have the truncated field, and that's going to be 1 bit. We have 0 for non-truncated, 1 for truncated. If we are setting this flag, that means that the reply exceeded 512 bytes, and only the first 512 bytes of the reply were returned. So remember why we started to do this. So UDP limitations is one, and IP fragmenting is another. The size, the lowest required size for MTU is 576 bytes. So what UDP did is went and reduced it down to the closest value without going over, so that we really try to avoid IP fragmenting because it's so undesirable from a UDP perspective. Now, if we need to go above 512 bytes, that's where we're going to just shift and use TCP, but we'll take a look at that here in just a bit. So then we have the RD bit, which is recursion desired, and that's again 1 bit, and that's going to be 0 for no recursion, 1 for recursion desired. If this bit isn't set, the reply will only contain information on what the other DNS servers to contact. So basically, if we don't set that, then we're going to move forward and we're going to act as our own recursive DNS server. We're going to reach out to other DNS servers and do that iterative process on our own behalf. So recursion available, again, 1 bit. 0 does not support recursion, and 1 supports recursion. If this is not set, this will force the client to go and do iterative queries on its own behalf. Then we have the Z-bit. This is 1 bit that's used for future use. Right now, it's always set to 0. AD is going to be authenticated, 1 bit, set to true if the information is authenticated. Then we have CD, which is checking disabled, which is 1 bit, set to true if the security checking is disabled. So we're going to talk more about this, the checking disabled, in chapter 18. Then we have R code, which is response code, and that's going to be 4 bits. So the common values here are going to be 0, which is no error, and 3, which is NX domain, which is non-existent domain. You can see more values for R code on page 522 in your textbook if you're curious. But the most important ones that I want you to remember are going to be 0 and 3. Then we have query count and zone count, 16 bits, answer count and update count, 16 bits, authority record count, update count, 16 bits, additional information count, 16 bits. So typically, if a query, the query count is going to be 1 and the rest are going to be 0. And then if it's going to be a reply, there's going to be at least 1 answer. So that's where we kind of gotten into in previous slides, saying that in the answer, authority record, additional information portions, there's going to be at least 1 record that's provided there. So this is going to be what our header looks like here. So we have our kind of fixed sizes, and then we have our various our variable sizes sections below there. So we have this is the DNS structure that we're going to be using. Overall, we'll go through this a little bit more, but this is generally speaking what it's going to look like. So the next portion that I want you to be familiar with is names and labels. So in the variable length sections, which are going to be at the bottom here, question, answer, authority, additional information, we have what we call a name. And so the name is going to be the domain name or the owning name. And then we have each name consisting of a sequence of labels. So we have data labels and we have compression labels. Data labels are going to be basically our kind of ASCII character representation, which are parts of the domain name. Then we have compression labels, which are basically pointers. So we have something that says we want to look at, we have a value here, and that means go look at elsewhere to get what this value is. Now that helps us save space in our variable sections, variable length sections to be more accurate. So it lets us point to the repeated use of a particular string. So for instance, if we see com over and over and over again, we can just keep adding in a pointer that says to look at com in a different location. And again, it's for repeated use of different values. So this is what data labels kind of look like. So we have ASCII characters that are included in here. And remember that ASCII characters are 1 byte per character. If you have more questions on ASCII, I'd recommend kind of look up what ASCII characters are and how they're created and how binary maps to ASCII. So I would just definitely take a look at that. Each label is going to begin with a 1 byte count that specifies the number of bytes that immediately follow. So the length can be from 0 to 63. And so typically this is going to be ASCII, but technically it can be Unicode. This, as a side note, a little bit of a tangent. So when we get into Unicode, that means we can kind of use funky looking characters because the character set is expanded significantly. So this is how some adversaries or some attackers will make phishing domains look legitimate. They'll use a character that looks like an O but actually isn't. Or they'll make it look like a C, but it's the C that has the little squiggly on the bottom of it. That is from other alphabet sources or Russian characters or what have you. But basically, since we're extending with Unicode, we can do some kind of funky things there and kind of trip people up. But typically, it is going to be ASCII characters that are here. So if we go down to the bottom, we can see the numbers 3, 7, 3, and 0. So 3 is going to be the number of bytes after that are going to be the length of that label. So for instance, 3 is going to be the byte length of www. Again, ASCII characters, 3 characters, 3 bytes. Same thing with Pearson. You put a 7 in front of that because there's going to be 7 bytes after. So now the max range is 63 characters. So any subdomain or domain or host name can only be 63 characters long. So that is going to be a limitation for domain names. Now, at the end of this data label, there's a 0, and that's just going to indicate that that is the end of our entire data label. And so this is how, in a DNS record, we would see the way that this domain is listed within the record itself. So then we have compression labels. So again, this is used to point to a different portion of the label so that we can actually save space. And so the way that we do this is in the label type field there, you see it set to 192. So that means basically setting the first 2 bits to ones, and then you have a 14-bit offset. And then with that 14-bit offset there, we are able to basically point to where that compression target is. So for instance, this is an example of usc.edu and ucla.edu. And so what we do with that 192 and 4 is we basically say where to point back to. So in this case, we are pointing back to the 4th byte. And so that is going to put us right into where we get into edu. And so, the edu portion. So that's basically saying ucla.edu. And so now you can see kind of how it saves some space. I wouldn't worry at this point too much about having to be able to manually generate an offset and things like that. Just know that compression labels are pointers, and generally speaking, kind of what it would look like with that label type with the 192. So DNS, TCP or UDP? Well, why not both? So DNS, like I said before, can leverage TCP or UDP on port 53. And so when do we use each? Well, I also said that the minimum MTU of hosts is going to be 576 bytes. So DNS set their maximum payload via UDP to be 512 bytes. If we go over 512 bytes, then we're going to switch to using TCP instead of UDP. And again, this is from because of the IP fragmenting issue. And so TCP has much more efficient ways of handling fragmenting than IP does. And so this is why we choose to use TCP. And then even TCP is going to typically move forward and say, don't fragment this. We're going to do some MTU discovery to determine what MTU or what payload size to use for our TCP segments. And we're going to talk about that in the next lecture, or the first TCP lecture that we have. If a reply comes back and it's going to have the truncated flag set, the host might actually reissue the query using TCP instead of UDP. So remember, UDP sticking to 512 bytes. So if we want to get all that information back, we need to switch to TCP and reissue that request. Additionally, if we're doing a zone transfer, which we refer to as a DNS notify, we will use TCP if it goes over 512 bytes. In a lot of cases, this is where we are going to definitely use TCP because things like full zone transfers are going to be pretty large in most cases. And so we're just going to use TCP because, again, we don't want to fragment and we want to have reliable information being transferred between primary and secondary DNS servers. So it's obviously important to have accurate information, good error checking and things of that nature, so we use TCP for those. Incremental zone transfers might start as a UDP type of communication, but then they might change over to TCP if needed. So again, if it gets large, if we're having issues with errors, then we might want to use TCP for that. Just a reminder, so if UDP is being used, the application layer is going to be responsible for timeouts and retransmission. So the transport layer protocol, UDP, cannot do any of that for us. So we need to rely on the application to know what's good and what's bad, and ultimately keeping track of all that. So question or queries and zone section format. So the overall section size is variable. So these are now sections, and these are the variable parts of our DNS our DNS message. And so the first part of the section is going to be variable. The second and third parts are going to be 2 bytes in length. So we have the query and zone name. This is going to use our data and compression labels that we talked about. And then we're going to have a zone type, and we're going to have a zone class. So the resource record type, and we're going to talk about this more in just a few slides, but that's going to be a 16-bit field. And then we have the query and zone class, which is also going to be a 16-bit field. And the most common values are going to be 1, 254, and 255. And that's going to be internet class, no class, or all classes, respectively. So this is going to be what that kind of section looks like in the DNS query. You saw variable, 16-bit, 16 bits. So then we have answer authority and additional information sections. So that's going to contain sets of resource records. So as I mentioned before, DNS is all about resource records. It's going to be about providing those mappings of host names and other information to IP address, or just other types of resource records for you to use on as part of your client. There's the name field, which is going to be the domain name for which the following resource records correspond to. The type, which is going to be one of the resource record type codes. Class, again, 1, 254, 255, same as the previous section. And then in this case, we have TTL. So it's going to be the number of seconds that the DNS record can be cached for. And so, again, there's pros and cons to both. Sometimes it's really low, and sometimes it's really high. We also have RD length, which is resource data length. It's going to be the number of bytes in the R data field. And then we have R data, and that's going to be the variable length, which is going to be dependent on our resource record type. That's going to be the data in our resource record. So this is going to be what that field looks like. So we have that name, again, variable. And then we have type and class, 16 bits each. And then TTL, which is going to be 32 bits. RD length, which is going to be 16 bits, and then the data, again, is going to be variable. So we have resource record types. So there's going to be 3 main categories for resource record types. It's going to be data types, there's going to be query types, and meta types. So data types are going to be convey data stored in DNS. There's going to be IP addresses, names of name servers, etc. Then we have query types. Normally, these are going to be the same as data types. There's going to be a few additional values that are available to us. And then we have meta types. And this is going to designate kind of the transient data that's associated with a specific DNS message. So these are going to be the important resource records that I would like you to be very familiar with. So we have A, NS, CNAME, start of authority, pointer, MX, TXT or text, quad A or AAAA, and then the service record. So we'll talk about each of those in depth now. So we have A records. So A records are going to be our traditional DNS record. They're a host to an IPv4 address. Okay, so keep that in mind. A is IPv4, host to IPv4 address. Then we have the quad A record, which is going to be a host to IPv6 address. And then we have a CNAME. This is going to be like a nickname for an A record or an alias. And so this is going to map another host name to the A record. So for instance, for A, we might have webserver1.google.com. And that's going to map to some IP address. Well, we can also say that www is a CNAME or an alias for webserver1.google.com. So it's something, it helps with things like load balancing, to be able to provide an alias record that points to a bunch of different records. And so again, it's an alias, it's a nickname, it's for something that's able, or that you want to use to not have to be so hard for a user to remember, or it's just a way to make a more user-friendly alias and maintain that versus having to maintain an A record all the time, or have users using A records. So it's just a way to make it a little bit more user-friendly and more transparent from an administration perspective. Then we have name servers. And so name server records are going to contain the names of the authoritative servers for a particular zone. So remember, we have these authoritative servers, and these authoritative servers are going to be what have the truest and best information for our zone. Well, when you go to a zone, you get to specify what the name servers are for that zone via the name server record. So then you have pointer records. And so pointer records are going to be a reverse DNS lookup. So pointer records can be very helpful, but they can also be potentially a security risk as well. So in a lot of cases, with a pointer record, we're going to map an IP address to a host name. But since DNS is going to be focused on mapping host names, we have to do it in a little different way. So what we got to do is basically we have a host name. The host name is going to be derived from an IP address, but then use a domain of .in-addr.arpa as the domain there. So in this case, we have first octet, second octet, third octet, and fourth octet. That's going to be from your IP address. So basically, you're taking your IP address, you're flipping it around, doing a 180 with that, and then putting a domain of in-addr.arpa. And so when you do a DNS request for that particular host name, then it's going to use that pointer record mapping to obtain the IP address of the it's going to obtain, the host name for that particular IP address. So we're going from IP to host name, which is backwards. So pointer records are helpful from that perspective if you ever have an IP address and need to know what host name it maps to. However, if we have pointer records that are associated with every host in the domain and every IP address in the domain, I, as an adversary or an attacker that is trying to enumerate all hosts in your environment, could simply write a quick script to iterate through all IP addresses in your environment and determine what the host name mappings are for those IP addresses. So I could literally enumerate your entire environment through that process. So it's a fine balance on determining what needs to have a pointer record lookup and what does not. So then we have start of authority. So start of authority is going to provide the authoritative links between portions of the DNS namespaces and servers that provide the zone information. And so this is going to kind of give us information on the official, the host providing the official database, the responsible party's email address, zone update parameters, default TTLs. So this is going to give us a lot of kind of the configuration information of the DNS zone. And then we have mail exchangers. So mail exchangers are going to point to the default or the mail servers for our domain. So when we send emails to specific domains, we don't have that IP address cached, then we will have to do a DNS request looking for the MX record or the mail exchanger record for that particular domain, so we know where to send email to. So again, we can't email if we don't know what the IP address of the mail server is. And we can't figure out what the IP address of the mail server is without being able to do a DNS request for the MX record. So then we have two resource records that are a little bit more interesting. So we have service records. So it's a generalized record type. It's going to indicate the hosts that are used for a specific service. So for instance, LDAP. With Active Directory would be an example of an SRV record and where to go for the Active Directory service. So it's a generalized version of kind of an MX record. So MX record is specifically for email, but with SRV records we're able to kind of just define specific services and then different clients can figure out where to get that information. So then we have text records. Now text records are even more generalized, and they're more freeform, and they basically contain strings of information, so it can be customized. So basically, we can set text records to hold any number or any different information that we want with our various strings. So for instance, we use an SPF record, which is going to be a form of a text record for email protection. So we put specific information in this text record, and then email servers will validate this information to the domain to verify that this is an expected sender for this particular domain. So let's take a look at DNS in Wireshark and see how some of this process works. So I'm going to start a new capture here. Get the boot P out of there, and I'm going to make sure that we are actually obtaining information here or getting some packets. Takes just a second. You can do it. And packets any day now. Cat videos. Come on, you can do it. Send something. Alright, I'm going to trust that it's just going to send something. So what I'm going to do here is I'm going to clear my screen, and I'm going to go ahead and do an IP config, and then I'm going to flush DNS. And so what this is going to do is it's going to get rid of all the DNS records that I have in my cache. Okay, so I successfully resolved that. So now what I'm going to do is I'm going to do an NS lookup, and I'm going to do www.google.com. Okay, and so what it does here is it's going to go through and it's going to say, look, I found www.google.com. It's at 172.217.9.68. So now let's go back to, actually, you know what? Let's do another one. Let's do NS lookup, and we're going to do Reddit, www.reddit.com. Boom, and then I got my DNS information there, and so I got 151.101, 1.140, a bunch of 140s in there, www.reddit.com. Notice that the alias is www.reddit.com, but this answer here is reddit.map.fastly.net. So another thing here, non-authoritative answer. So although my cache didn't have reddit.com or www.reddit.com or www.google.com, my DNS server likely did, because I'm an avid Googler and an avid Redditor. So that information is going to be in my DNS server's cache. So those are still non-authoritative answers. Now, if I were to try to query, let's say, www.cisco.com with an NS lookup there, I again get a non-authoritative answer because it's cached somewhere. So typically, I'm not even ending up at the DNS servers that I need to. But anyway, let's head back to Wireshark here, and here's all my packets. They were hiding because I didn't take my, I didn't remove my filter completely. So we stopped here. We got a whole bunch of stuff going on here. So if we change this to be DNS, we can see a whole bunch of queries that have been done, and including some pointer records. So that's pretty cool. So anyway, one easy way that we can actually start looking through some of this is we can do a find packet and come in here and say string, and we can do reddit.com. And then with that, we can see where some of these queries start. So anyway, if we come in through here, we can just start seeing start to finish kind of how these go. And so let's just kind of walk down through a couple of these. So if you see, so you have standard query, right, is for a record www.google.com. So we can come in here and see this information. So we have, again, our layer 2, layer 3, layer 4, and then our layer 7 information through our DNS query. So we have flags and we have queries. So the flags, we have 0, so we have the message is a query. Opcode, standard query. Truncated, not truncated. Recursion desired, do not query recursively. You have your Z, which is reserved, and then non-authenticated data. Unacceptable. I'm not sure what the unacceptable part is, but it's not authenticated. So we have one question here, and then we don't have any answers, because again, this is the query. So if we go down to the query, we are querying for www.google.com, and in my case, since I'm here, I'm still querying for local domain, which is kind of handled at the DNS server. But again, the type is going to be a host address. So we have a lot of that information there. So let's go to the next DNS packet we have. And so now we have the response. So we have standard query response, no such name as www.google.com.local domain, right? So this is just kind of saying, hey, you added a local domain. That's kind of weird. So let's just skip over that. So we're going to go to www.google.com. Okay, so do query recursively. So this is our actual DNS record that we use to query out to www.google.com. And so again, non-authenticated, but we get into the questions, and then the queries are this time the right one, which is going to be www.google.com. And then it's a type of A record. So again, this is a host name to an IPv4 address. So then let's go to the next one, and this is going to be the response. So we have our flags in this case. So we have a flag of set for response. It's a response message, opcode, standard query, authoritative. So we're not getting an authoritative response for this. It's coming from somewhere that had it cached. Not a truncated message. We did this query recursively. The recursion available. So this is where we're seeing the DNS server saying, yep, I can do recursion. And so that's all good to go. And then you have the answer authenticated and non-authenticated data again. And the reply code. There's no error. Perfect. Sounds good. We did this great. So there's the one question and then there's the one answer. So the query was www.google.com for an A record. What is the IP address? And in this case, the answer is going to be for www.google.com. We have 172.217.9.68. Awesome. So now we just did exactly what we were supposed to do. We were able to resolve the information for www.google.com to the IP address. And then even better, we have our time to live, 205 seconds. So that is going to tell us exactly how long that query can live in our cache until we need to look for it again. So then if we look at the Reddit query that we did, and I want to find the response to that, which is here. So we have, and what I wanted to show you here is just that we get a bunch of different answers here. So remember that there could be more. We said before that it could be one or more answers. This is an example of one or more answers. So we have, in this case, 1, 2, 3, 4, 5 answers. And so we see here that we have a CNAME record, so we have that alias, and then we have multiple DNS record resolutions there, which is going to be the host name to those IP addresses. And then again, time to live, 29. So just a way to look at that. So this is how you look at DNS in the environment.